All right, we're going to continue our discussion of number systems. With binary. Binary is base 2. Now, from last class, we learned that the number of the base is the number of symbols that you can use to represent numbers. So base 2 has 2 symbols. Zero and 1. Representing a number greater than 1, you need to add columns like you did in the decimal system. When you got to 10, you have to roll back over to 0 and put a 1 in the next column. Same is the case with base 2. So it starts with 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, etc. That's counting up. That's binary, and the decimal equivalent is 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, run out of symbols, so you roll over to 0 again, add a 1 to the previous to the next left column, gives you 1, 0, add 1 to get 3, 1, 1, add a 1 to get add 1, you roll over to 0, carry the 1. 1 plus 1 is 2, which is not possible. So you do 0, carry the 1, and then a 1. Okay? So, like the base 10, is to convert to base 10, a binary number, you have the number of the base raised to the 0th power, number of the base raised to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, etc. Those are the values of the different positions of the numbers, of the symbols. So, if you have a number, say 1, 0, 1, 1, 0 in binary, two to the fourth is 16. So that's 116 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. So the 16 is 2 to the fourth. 2 to the third is 8. 2 to the second is 4. 2 to the first is 2, and 2 to the 0 is 1. And then you multiply it by the value of the symbol. 1 times 16, 0 times 8, 1 times 4, 1 times 2, 0 times 1. So the equivalent decimal is 16 plus 4 plus 2, which is 22 in base 10. So you have, was 1 0 1 1 0, base 2 is equal to 22 base 10. It really is that simple. It's not a difficult thing. You just expect it to be difficult and overthink things. A lot of students I have had overthought and made mistakes on quizzes and tests because they overthought the problem. It's just the power of the position, the power of 2 of the position, so the 4th position, the 0th, 1st, 2nd, 3rd, 4th positions, times 1 if there's a 1 there, 0 if there's a 0 there, and then you add all those up. So I realize that for those of you that have had digital logic already, you probably have covered this material before. But to convert a number from decimal to binary, let's go ahead and give an example. Let's say 73. And let's over here put the powers of 2. 64, 32, 16, 8, 4, 2, and 1. Get everything? Yeah. 1, 2, 4, 8, 16, 32, 64. Okay. So what's the highest power of 2 that goes into 73? 64. So you take 64, you subtract it from 73, which gives you, what, 9? You put a 1 in the 64's position. What's the next, the highest power that'll go into 9? 8. So subtract 8, gives you 1, and then 1 gives you 0. So there's no 32s, there's no 16s, there's an 8, no 4s, no 2s, but there's a 1. So there is your answer. 73 base 10 is equal to 1001001 base 2. Where people get tripped up a little bit is when you get to negative numbers. Computer lines will have 1s and 0s. A line is either high or low. High is a 1, low is a 0. So they can carry the ones and zeros, but they can't carry a sign like plus or minus. So a negative number in binary, let's go ahead and do my negative 73. To make it a negative number, you convert it to binary, which we've already done, the 73 into binary. Then you add enough zeros to the beginning of it to make it an even number of bytes. A byte being 8 bits. So we got 4, 7, so we need one leading 0 to make it an 8-bit number. Okay? Now, to make it negative, you do what's called a 2's complement operation on it. The 2's complement is flipping the bits. So zeros become ones, ones become zeros. 0 becomes 1, 0 becomes 1, 1 becomes 0, so on down the line. And then you add 1 to it. So you add 1, and that gives you 1, 0, 1, 1, 0, 1, 1, 1. That is equal to negative 73 base 10. So when you get into math, all you have to do is worry about addition. Addition, like we did here, is just simple. 1 plus 0 is 1. 1 plus 0 is 1, so on and so forth. And what I showed you on the first board. Subtraction is just adding a negative number. So for subtraction, you make it a negative number, and then you add it to the first number. That's all subtraction is adding a negative number. Multiplication is just repeated addition. Division is just repeated subtraction. So all you really need to worry about is addition. And in digital logic class, you learn about adders and that sort of thing, the hardware that implements the add operation. So typically in computers, there's more than 8 bits. There'll be 16, 32, 64 bits. Quite a bit. But you'll notice that the first bit on a signed 2's complement number, the first bit is the sign bit. A 0 indicates that it's a positive number. A 1 indicates that it is a negative number. The flipping the bit and adding 1 works also to convert a negative number into a positive number as well. So let's just use this last one here, this example here. 0, 1, 0, 0, 1, 0, 0, 0, add 1, and that gives you 1, 0, 0, 1, 0, 0, 1 with a leading 0. And as you can see, this matches that. And from there, you can convert that to decimal, just knowing that you can. It was started out as a negative number here, and add the sign in front of the decimal number to indicate that it is, in fact, negative 73. So for how many of you is this new? Just a few, okay. But I know there's not very many freshmen in the class, but yeah, it's a fairly simple system. In digital logic, you'll learn how to implement this easily in logic, so the wires can do it. So, how are we doing on time? All right. That's about it for binary. That's how you convert from binary to decimal and decimal to binary. Convert a negative number to a positive number, or a negative number to a signed 8-bit complement, 2's complement binary number. Pretty straightforward. Just remember that a base has that many symbols. So a base of 7 will have 7 symbols. Base 10 has 10 symbols. Base 2 has 2 symbols. Another system that you might run into if you work on legacy systems is octal, which is base 8 has 8 symbols. So 0 through 7 are used for octal. Any questions? Need more examples? Or think you're good with that? So, all right, well, just the one class this week. We'll make it easy and pack up for the day. See you again on Monday, where we will cover hexadecimal.